Here is a combined summary of the 4 pages. The proposed FPGA accelerator tackles issues of high on-chip, off-chip memory overhead and low computational efficiency in existing lightweight convolutional neural networks, LWCNNs, accelerators. The novel multi-computing engine (CE) architecture employs a streaming architecture with hybrid CEs, minimizing off-chip memory access while maintaining a low cost of on-chip buffer size. A balanced dataflow strategy is introduced to enhance computational efficiency by improving efficient resource mapping and mitigating data congestion. Analysis of memory access patterns and computational loads of LWCNNs reveals the need for an optimized architecture that minimizes memory access costs while ensuring high computational efficiency. The ratios of deepwise separable convolution (DSC) and shortcut connection block (SCB) to standard convolution (STC), in terms of multiply accumulate (MAC) operations and feature map (FM) memory access are calculated, highlighting the significant reduction in operations by DSC and SCB compared to STC but at the cost of increased FM access. The distribution of FMs and weights in LWCNNs is examined, noting that the number of parameters and weights varies from layer to layer, with shallow layers generating larger FMs and consuming more parameters, while deep layers produce fewer FMs but require massive parameters. Related works on LWCNN accelerators are reviewed, including those that perform convolutions within a unified computational element (CE), those that develop dedicated CEs for DWC processing, and those that employ a multi-CE architecture for LWCNNs. However, limitations in these approaches are identified, such as low computational efficiency, high power consumption, and suboptimal memory footprint. The proposed streaming architecture with hybrid CEs comprises 2 types of CEs: feature reuse computing engines, FRCEs, for shallow layers, and weight reuse computing engines, WRCEs, for deep layers. FRCEs eliminate off-chip memory access by storing all weight data on chip, while WRCEs minimize external memory traffic for weight data through a fully reused weight scheme. The proposed accelerator reduces on-chip and off-chip memory utilization while enabling high computational efficiency for LWCNN acceleration. The research proposes novel approaches to reduce on-chip memory occupation and off-chip memory traffic in streaming architectures. It introduces 2 types of processing elements: FRCEs and WRCEs, each with distinct data reuse schemes. FRCEs focus on fully reused feature maps, while WRCEs emphasize fully reused weights for deep layers. The design targets shallow layers for FRCEs and deep layers for WRCEs. The paper also introduces a ping-pong structure-based global FM buffer to reduce off-chip memory traffic. The comparison between FRCE and WRCE is summarized in Table I. The proposed memory-optimized streaming architecture for LWCNNs aims to enhance computing efficiency by addressing the limitations of current streaming accelerators. It uses a fine-grained parallel mechanism and a data flow-oriented line buffer scheme to promote overall throughput and reduce data congestion. The architecture significantly enhances the computing efficiency of STC and DWC layers with diverse padding locations and strides. The proposed research paper presents a resource-aware memory and parallelism allocation methodology for optimizing the performance and compatibility of a streaming neural network accelerator. This methodology is decomposed into 2 parts: a balanced memory allocation algorithm and a dynamic parallelism tuning algorithm. The balanced memory allocation algorithm iteratively determines the number of FRCEs based on the memory evaluation model to minimize off-chip memory access while meeting on-chip memory constraints. The dynamic parallelism tuning algorithm adjusts the parallelism of each layer to balance computing time among all CEs. The authors evaluate the effectiveness of the proposed architecture using 4 representative LWCNNs and implement Mobile Net v2 and Shuffle Net v2 on the Xilinx ZC706 board, showing significant reductions in on-chip memory size and off-chip memory access compared to other streaming architectures. The research also discusses a novel streaming architecture for LWCNNs, presenting a hybrid data reuse scheme that reduces SRAM consumption by 81.37% and achieves an average FM access reduction of 98.07% compared to existing schemes. The evaluation process focuses on the theoretical throughput and scalability of the FGPM, demonstrating a significant improvement in MAC efficiency and outperforming several existing solutions in terms of performance and computing efficiency. The research paper presents an efficient and scalable lightweight CNN, LWCNN, accelerator, featuring various memory and computing optimizations. The proposed design achieves state-of-the-art performance, with a throughput of up to 2092.4 fps and a peak efficiency, PE, of up to 94.58%. The hybrid CE architecture eliminates off-chip access for intermediate feature maps, reducing memory occupation and improving computational efficiency. The balanced dataflow strategy optimizes resource allocation and on-chip bandwidth, resulting in high MAC efficiency. Additionally, the design realizes a competitive DSP utilization of around 95% due to the scalable architecture and dynamic parallelism tuning algorithm. The paper also provides a comprehensive comparison with previous mobile Net v2 accelerators, demonstrating better performance, memory occupation, and energy efficiency. The authors cite various works related to CNN acceleration, FPGA-based designs, and optimization techniques for deep neural networks, highlighting the significance of the proposed design in the field of LWCNN acceleration.